Hello everyone and welcome to This Explainer. Today, we are taking a deep dive into software engineering, and we'll be focusing entirely on interaction models. It's a fascinating topic, so grab your notebooks and let's get started.
Okay, let's dive right in. Here is our roadmap for today. We'll start with an introduction to interaction models, then move into use case modeling, followed by sequence diagrams, and we'll wrap it all up with a summary and exam focus to make sure you're completely prepared for your tests.
All right, Part 1, an intro to interaction models.
To really understand why we need interaction models, we need to think back to context models from Chapter 4. You might remember that context models define our system boundary. Well, once that boundary is set, we have to actually map out the system's behavior. And all systems involve interaction of some kind. This could be user interaction, where a human is providing inputs and getting outputs. It could be an interaction between the software we are building and other external systems. Or it could even be internal interactions between the components of the software itself. So why do we do this? Modeling user interaction helps us nail down essential user requirements. Modeling system-to-system interaction acts like a safety net, highlighting potential communication problems before we even write a single line of code. And modeling component interaction? That helps us guarantee that our system structure will actually deliver the performance and dependability we need.
Moving swiftly on to Part 2, use case modeling. Use case modeling is a brilliant tool. It was originally developed back in the 1990s, and we primarily use it to model interactions between a system and external agents. Now, whenever we encounter technical terms, it is absolutely crucial that we define them first. So what exactly is a use case? Basically, it represents a discrete, specific task that involves some kind of external interaction with a system. Think of it as a simple, plain English description of what a user expects the system to do during a single interaction. Next up, what is an actor? Now listen closely, because this is where students almost always make a mistake in exams. An actor is represented as a stick figure, but it is not always a human being. An actor can be a human user, sure, but it can just as easily be a piece of hardware or an entirely different external software system.
What's really interesting here is how incredibly simple the visual notation is. Take a standard transfer data use case from a typical medical software setup, for example. The task itself is represented by a named ellipse in the middle, transfer data. The actors involved are those stick figures on the sides. On the left, you might have the medical receptionist, it's human. But on the right, you could have a patient record system, which is an entirely non-human software database. The lines simply link the actors to the interaction, showing that data is being uploaded from one system to this broader patient record system.
But here is a golden rule you absolutely must remember. A use case diagram alone is never enough. The visual gives us a fantastic quick overview, but it really lacks the nitty-gritty detail needed for a complete interaction description. Because of this, a diagram must always be backed by a tabular description. You need a table that spells out exactly what the stimulus is, like the receptionist actually issuing the command. It needs to detail the expected response, say a confirmation of success or an error message. It even needs to include crucial comments, like making sure the receptionist actually has the proper security permissions to perform the action in the first place.
Now, in a real complex software system, a single role is going to perform a whole bunch of discrete tasks. It would be a complete mess to leave them all separated out. So we group related tasks together into what we call a composite use case diagram. For instance, if we look at all the use cases for a medical receptionist, we can see that this one human actor can initiate registering a patient, unregistering a patient, viewing patient info, and transferring data. Grouping them like this makes it incredibly easy to see the complete scope of responsibilities for any given actor at a glance.
So, the crucial point to take away here is understanding the difference between the model we just learned and the one we are about to learn. Use case models give us the big picture. They tell us exactly what tasks are happening and who is involved. But they don't tell us how the system executes those tasks under the hood. And that is exactly where sequence diagrams come in. They are our chronological blueprint, showing us step-by-step how objects in the code actually pass data back and forth to achieve that task. Just to recap quickly, use cases are the what and the who. Now let's explore the how and the when.
Which brings us to Part 3, sequence diagrams.
Shifting our focus from those external systems right down into the internal components, let's look at how objects communicate over time. A sequence diagram in the Unified Modeling Language, or UML, is primarily used to model the chronological interactions between the actors and the objects in a system. The absolute most important concept here is the lifeline. A lifeline is a dotted vertical line drawn downwards from an object. It literally represents the lifespan. the time that a specific object instance is alive and actively involved in the computation. Whenever you see a solid rectangle sitting on that dotted line, it means the object is actively processing something at that exact moment in time.
Let's apply this to a real example, like a task where we view patient information. This perfectly illustrates how things work in practice. If you look across the top of a sequence diagram, you'll see your actor, maybe the medical receptionist, alongside your system objects, like a patient info interface, a database, and an authorization system. From every single one of these, you'll see those dotted vertical lifelines extending downward. The horizontal arrows passing between them, those represent the actual messages or method calls being passed from one object to another. And remember, this is vital. You must always read sequence diagrams from top to bottom because time flows downward.
Let's step through exactly how you interpret these diagrams, especially when things get a bit more complex and logic gets involved. We've seen the actors, the lifelines, and the messages, but often you'll see a large rectangle labeled ALT. ALT simply stands for alternatives. This is how we model conditional logic. It's essentially an if-else scenario in programming. Inside that ALT box, you will find conditions written in square brackets, separated by a dotted line. For example, if the condition authorization OK is met, one specific set of messages is sent. Else, if authorization fail is triggered, an entirely different error message sequence is sent. It's just a clean, visual representation of your code's branching logic.
Before we leave sequence diagrams behind, there is one more advanced feature you really should be aware of. Sequence diagrams don't just show existing objects passing messages back and forth. They can actually model dynamic object creation during an interaction. For instance, imagine a user requests to upload patient data. The sequence of operations might actually trigger the creation of a brand new summary object in memory to hold that summarized health data just before it is sent over the network to a national database. It's a really powerful way to show the life cycle of data structures as your software runs.
Finally, Part 4, Summary and Exam Focus.
We've covered a lot of technical ground today, so let's lock in those key facts you'll definitely need for your upcoming exams. Number 1, watch out for the trick question. Actors and use cases can absolutely be hardware or software, not just human beings. Number 2, a use case diagram alone is incomplete. It must always be supported by a detailed tabular description. Number 3, always read sequence diagrams chronologically, starting from the top of the page and working your way to the bottom. And number 4, make sure you understand that alt boxes represent alternative options, using square brackets to show conditional logic, like authorization OK versus authorization fail.
So we have successfully modeled the behaviors in the interactions. We know what the system does and chronologically how the objects talk to each other to make it happen. But I want to leave you with a question to ponder. How do we actually design the static, structural architecture of these object classes before they even start interacting? Well, that is exactly what we will uncover in our next session on structural models. Thank you so much for joining me in this explainer. Keep reviewing those diagrams, practice reading them top to bottom, and I will see you next time.